Welcome to the Deep Dive, the show where we slice through complex research and hopefully deliver those aha moments that genuinely expand your understanding.
Uh-huh.
Today, we're plunging into a piece of research that honestly feels almost like science fiction. We're talking about an AI system designed to help, well, build other AI systems.
It's truly fascinating stuff. Imagine you're a data scientist, maybe a brilliant one, aiming high, perhaps like those Kaggle grandmasters.
Right.
You've got this groundbreaking idea, maybe an AI that can predict stock market shifts with like unprecedented accuracy.
Or diagnose diseases from medical images faster than human experts.
Exactly, or even spot subtle climate changes from satellite data. The potential is just immense, isn't it?
Absolutely. The dream is always to create something world-changing. But the reality, as anyone who's tried knows, is that transforming that brilliant concept into a high-performance, working AI model isn't just hard. It's often a grueling marathon.
It really is. And for anyone who's even dipped a toe into the world of machine learning, you understand this pain firsthand. Think about those Kaggle competitions.
Yeah, the Olympics of data science, basically.
Pretty much. They're not just coding challenges. You have elite data scientists from all over the globe pouring months, literally months, of their lives into these things.
Right.
Battling it out to innovate, to refine, to squeeze every last drop of performance out of their models. It's incredibly intensive. It demands not just technical skill, but a deep well of creative problem solving and just relentless iteration.
It's a perfect encapsulation of what the authors of the paper we're looking at today call machine learning iterative development, or MLD. That relentless, multi-step process of crafting advanced AI. And it's brutally difficult for humans. So here's our what-if scenario, the big question for today. What if an AI could step into that arena, not as another competitor, but as your most brilliant, tireless assistant? What if it could navigate that immense complexity, sift through countless possibilities, and pinpoint winning solutions far faster than any human typically could? What if an AI could help you build another AI?
That's precisely the bottleneck this cutting-edge research tackles. Building those high-performance machine learning models, as we said, it's this multi-step, expert-intensive thing. It's not just writing a few lines of code. It's incredibly time-consuming, can be prohibitively expensive, and demands a vast, vast array of specialized skills across the entire pipeline.
Right.
We're talking about everything from the initial meticulous data pre-processing, cleaning, transforming, preparing raw information.
Which is already a huge job.
Huge. Then selecting the optimal model architecture, fine-tuning sometimes hundreds of hyperparameters.
And knobs and dial.
Exactly. And then iteratively refining the underlying code, sometimes down to individual lines.
Yeah.
Each one of these steps is almost a discipline in itself, requiring unique expertise.
And we have seen incredible advancements in AI tools meant to help, right? Like large language models, LLMs, or even traditional automated machine learning, AutoML. But they still hit some pretty significant walls, don't they? Especially with these really deep, complex, maybe even novel challenges.
They do. For instance, LLMs are fantastic at generating code. We've seen them write websites, games.
Sure.
But as the authors of this paper, it's titled MLE-STAR, an LLM agent for machine learning iterative development, point out in their introduction, these LLMs often lack the deep systematic exploration capabilities you need for truly groundbreaking or high-performance ML solutions.
Okay.
They can struggle with adapting to very specific tasks that weren't, heavily represented in their training data. And there's always the concern of implicit biases they might have picked up.
Right, biases from the data they learned from. And what about AutoML?
Well, AutoML has definitely made great strides in streamlining certain parts of model development, but it typically operates within, let's say, predefined search spaces.
Okay, so it works within known boundaries.
Exactly. It's great at optimizing within a known set of parameters or model types, but it's not really designed for the kind of open-ended innovation and, frankly, creative problem solving you need to win something like a Kaggle competition.
Where you often need to go beyond the standard playbook.
Precisely. Finding truly novel approaches or unexpected solutions, that's a crucial limitation. AutoML is, you could say, like a sophisticated GPS that finds the fastest route on existing roads, but it can't design new roads or bridges where none exist. It needs that predefined map.
Okay, so that sets the stage perfectly. Enter our protagonist, MLE-STAR. The system designed to shatter those limitations. This isn't just another code generator. The paper presents it as an advanced AI agent, engineered from the ground up to automate and, crucially, significantly enhance the entire machine learning engineering workflow. It's AI building AI.
And its core innovation, as the authors really highlight, is this dual approach. It combines intelligent web search, basically finding and using existing state-of-the-art knowledge and best practices, with targeted refinement. That means iteratively improving specific, critical parts of a potential solution.
So, learn from the world, then optimize intelligently.
That's the essence. This combination lets it explore broadly, drawing on the collective wisdom out there, and then optimize deeply, focusing its efforts where they'll have the most impact.
And that's exactly what this deep dive is all about. We're going to unpack how MLE-STAR works, explore the truly surprising results it achieved seriously, wait till you hear them, and discuss what its implications are for you. Whether you're actively building AI models, managing a team that does, or you're just really curious about the future of automation and how we develop cutting-edge tech.
Yeah, let's get into it.
So let's unpack this.
Okay, let's really dive into the context here, because understanding the broader landscape of machine learning automation is absolutely key to appreciating what MLE-STAR brings to the table.
Right, the bigger picture.
Exactly. When we talk about machine learning engineering, it's so important to understand it's far more than just, training a model on a data set. It covers the entire pipeline, every single stage.
From start to finish.
From start to finish. You begin with data ingestion, meticulous cleaning, because, garbage in, garbage out.
Always.
Then feature engineering, where you transform raw data into features models can actually learn from effectively. That's often an art in itself. After that, model selection, choosing the right algorithm. Then hyperparameter tuning, tweaking all those knobs we mentioned. Then, of course, model training, rigorous evaluation, and finally, the often underestimated challenge of deployment.
Getting it out into the real world.
Right. And each of these stages involves tons of decisions, often complex, deeply interconnected, and it requires constant iteration, often for months, just to improve performance bit by bit. It's this sprawling, multidisciplinary effort.
It sounds like it needs a whole team of specialists, really.
Often it does, yeah. It demands a breadth of knowledge you usually only find in highly specialized teams.
So it's not just about coding. It's this long, winding, iterative process. Countless decision points where one small change early on could have massive ripple effects later. It sounds a bit like trying to solve a Rubik's Cube blindfolded, where each turn affects everything else.
That's a really apt analogy, and this is precisely where that critical gap MLE-STAR aims to fill comes into sharp focus.
Okay.
While recent LLM agents have been impressive, we've talked about them creating Minecraft mods, solving programming challenges like AlphaCode.
Yeah, we've seen some cool stuff.
Definitely. But the authors emphasize that these more generalist LLM agents often struggle with the specific, deep, and truly iterative exploration that's absolutely essential for getting top performance in complex ML tasks.
So they're good, but maybe not specialized enough for this kind of deep dive.
Exactly. The paper explicitly mentions this, citing other agents like DS Agent, while promising they can suffer from scalability issues and often need significant human effort for complex problems because, as the authors state, they demanded a manually built case bank.
Ah, so they needed humans to feed them examples first.
Right, which kind of limits their autonomy on truly novel problems. Existing LLM agents can handle general coding or well-defined tasks, but they often lack the ability to adapt, deeply explore, and innovate within the solution space for these specialized ML challenges that don't fit a pre-existing template.
Okay.
MLE-STAR is specifically engineered to address this specialized, iterative need. It moves beyond just generating code to truly automating and enhancing the ML engineering workflow itself, even in sort of unexplored territory.
That makes a lot of sense. So if existing tools are like general contractors who can build a house from blueprints, MLE-STAR is more like a super specialized architectural firm and an engineering team rolled into one. It can design and optimize a cutting-edge skyscraper from the ground up, and even handle the unexpected complexities during construction.
That's a great way to put it.
So drilling down a bit, what were the main challenges the authors were really trying to solve with this specific approach? Within ML engineering, what were the specific pain points driving this research?
The primary challenge, as the authors articulate it, is that multi-step, expert-intensive process of MLID itself.
Right, the core difficulty.
They were directly targeting the fundamental bottleneck, the extensive domain expertise needed for every granular step. data preprocessing, sophisticated feature engineering, hyperparameter tuning, deep code refinement, all of it. Existing LLM agents, while they can generate syntactically correct code, often rely too heavily on the knowledge baked into their training data. They struggle with true exploratory search within specific parts of the pipeline.
Okay.
The authors noted LLMs tend to prematurely move to other steps, for example, model selection or hyperparameter tuning, because they lack the ability to perform deep, iterative exploration within specific pipeline components.
So they jump ahead too quickly.
Yeah, such as experimenting with different feature engineering options extensively. This is crucial. It means a standard LLM often can't fully see or anticipate the huge impact a seemingly small change in one part of the code might have on the overall model performance down the line.
Got it. They miss the intricate dependencies.
Exactly. MLE-STAR was designed to overcome this directly. It seamlessly integrates sophisticated web search for external, state-of-the-art knowledge and combines it with a systematic, targeted refinement strategy. This allows for that incredibly deep, component-level exploration and optimization needed to really push performance boundaries.
Okay, let's get into the how then. This is where it gets really interesting. This multifaceted approach sounds incredibly sophisticated. How does it even begin to generate a solution? Does it just start from scratch every time?
Not at all, no. It starts by generating an initial solution, and this is where it brilliantly leverages the collective knowledge of the web.
Wait.
The process begins with ML-STAR using its LLM core to propose initial model architectures and approaches just based on the task description. But it's not just guessing.
Right.
Crucially, it then performs what the authors describe as web search. The paper clearly shows this initial phase where the system actively retrieves relevant, state-of-the-art code snippets and models from public resources.
So it's looking online for good starting points.
Exactly. If you look at the methods, the specific prompt they use for this web search explicitly tells MLE-STAR to find and integrate relevant, state-of-the-art code snippets and models from public resources. This means it's not just finding random code, it's intelligently searching for and integrating existing successful solutions and proven models from public domains. It gives itself this incredibly powerful head start by essentially building on the shoulders of giants the collective work of thousands of data scientists.
So it's like a super smart search engine for AI models, but it actually understands what it's finding. And it can integrate it meaningfully into a working solution. It's not just like copying and pasting from Stack Overflow.
Precisely. It goes far beyond simple retrieval. After that initial search, MLE-STAR engages in what the authors call candidate model search and merging.
Okay, merging.
Yeah, as outlined in Algorithm 1 in the paper. MLE-STAR meticulously evaluates all the candidates it retrieved. Then it strategically combines the most promising ones into a consolidated initial solution. The system uses a specialized agent, they call it a merger, to take these retrieved candidates and integrate the best elements to form a strong baseline. And this process is iterative itself. A merger keeps generating new candidates and merging them with the current best solution, constantly improving its starting score.
So it's refining even the initial idea before it really gets going.
Exactly. It's like gathering all the top blueprints from the world's best architects, analyzing them, and then intelligently combining their strongest features to create a master blueprint to start from. It ensures the starting point is already robust and informed by best practices.
That's a brilliant start. But the real magic, it seems, happens in the targeted refinement phase. Can you break down this iterative improvement engine? That sounds like the core of its innovation.
Absolutely. The targeted refinement is the core iterative loop of ML-STAR. It's clearly laid out in the overview figure in the paper. This is where the system performs targeted code block extraction and code block refinement.
Okay, code block, like specific chunks of the code.
Exactly. It doesn't just randomly tweak the entire program hoping for an improvement. Instead, it systematically identifies which specific parts these code blocks have the most significant impact on the overall model performance.
How does it figure that out?
This precise identification is guided by what the authors call ablation studies.
Okay, ablation studies. That sounds pretty technical. Can you explain that in a way that makes sense for us? Like, what's the intuition there?
Yeah, sure. Think of it like a specialized diagnostic test for an incredibly complex machine, maybe a high-performance race car engine.
Okay, I like that.
If that engine isn't running perfectly, a good mechanic wouldn't just randomly tighten bolts or swap out parts, right?
No, that'd be crazy.
They'd perform systematic diagnostic tests to pinpoint the exact component causing the issue. That's essentially what MLE-STAR does with its ablation studies.
Uh-huh.
The authors use a specialized agent, Ellable, specifically for this. What Ellable does is it systematically removes or disables certain components, these code blocks, within the existing solution.
Temporarily disables them.
Right, in a simulation, essentially.
Yeah.
And then it meticulously observes how the overall model's performance changes.
Oh.
So if removing a specific component causes a significant drop in performance, that tells MLE-STAR, hey, this part is incredibly important. We should focus our improvement efforts precisely here.
Okay, so it finds the linchpins, the critical pieces.
Exactly. It's like a surgeon carefully, systematically, maybe simulating the removal of one non-critical organ at a time in a safe environment to precisely understand which one is causing a patient's symptoms. It gives the AI incredibly precise insights into where to concentrate its refinement efforts for maximum impact, avoiding wasted effort on components that aren't critical.
So to stick with our mechanic analogy, it's like a specialized mechanic for AI models. Instead of randomly tweaking things, it runs diagnostic tests. These ablation studies finds the exact part of the engine of the code block that needs fixing or upgrading. Then it meticulously refines only that specific part. Is that basically it?
That's a fantastic analogy, Noah, and it's spot on. It precisely identifies the most impactful code blocks, and then it enters a deep, iterative refinement process for only those parts.
Okay.
And this refinement isn't a one-shot deal, it's truly iterative. It keeps improving the solution step by step. This continuous improvement is guided by another agent, a planner, which generates new refinement strategies,
Wow.
and a coder agent, which then writes the refined code based on those strategies. This systematic, highly targeted approach is what lets MLE-STAR achieve such high performance. It avoids wasted effort and focuses computational resources on precise, impactful optimization. It's intelligent design over brute force.
That's incredibly efficient, but it doesn't stop at just one perfect solution, does it? I remember reading it also uses an ensembling strategy. That sounds like it's trying to get the best of all possible world.
That's absolutely correct. MLE-STAR doesn't settle for just one excellent refined solution. Throughout its iterative refinement, it generates multiple strong candidate solutions.
Yeah.
Then it employs a sophisticated ensemble strategy, which is detailed in Figure 3 of the paper, to combine these multiple solutions.
Okay, like averaging them out. Or something smarter.
Smarter. The core idea is similar to how a diverse team of human experts, each with unique strengths, can collectively arrive at a better, more robust decision than any single expert could alone.
Right, the wisdom of the crowd idea.
Kind of, yeah. By combining the strengths and mitigating the weaknesses of various well-performing solutions, MLE-STAR often achieves even superior and far more robust final models. The authors specifically state in section 4.2 that this ensemble strategy is iteratively refined based on the performance of the previous strategies.
Whoa, so it learns how to combine solutions better over time, too.
Exactly. It's not just combining, it's intelligently optimizing the combination process itself.
So it's about collecting the best ideas from several internal experts it created and merging them into one super solution that's stronger and more resilient. That's a really smart way to ensure robustness.
Mm-hmm.
And you also mentioned some additional safety features, almost like built-in quality control modules. What are those, and why are they so crucial?
Yes, the authors included several crucial modules to ensure not just performance, but also the practical robustness and reliability of the generated solutions, which is paramount for any real-world use.
Absolutely.
First, there's a dedicated debugging agent. They call it AidBugger. Its job is to automatically identify and fix errors in the generated Python scripts.
Wait, it debugs its own code.
It does. This is absolutely vital because even sophisticated AI can produce code with subtle bugs that would stop everything. AidBugger acts as an internal QA, ensuring the code is executable and functional.
So it can actually fix its own mistakes in the code. That's truly impressive. It's self-correcting.
Exactly. Then there's a data leakage checker called a leakage. This module is incredibly critical.
Data leakage. That's when the model accidentally sees answers it shouldn't have during training, right?
Precisely. It prevents the model from accidentally cheating by incorporating information from the validation or test sets into its training process. Data leakage is subtle but pervasive. It can artificially inflate performance during development.
Making you think your model is great.
And then it performs dismally on genuinely new, real-world data. A leakage meticulously checks code blocks for potential leakage and generates a corrected version if needed. It ensures the performance is genuine generalization ability.
That's huge for trust. And the last one.
The last one is a data usage checker, a data. This agent ensures that all the relevant data provided for the task is actually used properly within the solution.
Ah, so it doesn't accidentally ignore useful information.
Right. Sometimes models or pipelines might unintentionally neglect certain features or parts of the data set, leading to suboptimal performance. Data verifies that all provided information is incorporated effectively, maximizing the potential of the data.
So putting it all together, it's not just about building a high-scoring model. It's about building a reliable, fair, and robust model, one that learns properly, fixes its own bugs, doesn't cheat, and uses all the data. That's really thinking ahead, building in self-correction and quality control right from the start. It sounds like it's designed for production readiness.
It really demonstrates a comprehensive and remarkably mature approach to ML engineering. It's aiming for not just high performance, but also practical viability and trustworthiness, which are non-negotiable in the real world.
This is truly mind-blowing. Okay, let's talk about the results. The proof is in the pudding, right? Putting MLE-STAR to the test, what were the key findings? What did this system achieve when it went head-to-head with some of the toughest ML problems out there?
The primary evaluation, as the authors meticulously detail in Section 4.1, involved testing MLE-STAR on 22 diverse Kaggle competitions. These came from the MLE Bench Lite dataset.
Okay, so real Kaggle challenges.
Yes, and this dataset is specifically designed to provide challenging, realistic ML engineering problems. It mirrors the kind of complexity and data variations you'd actually encounter. These aren't toy problems. They're high-stakes challenges, where human experts often spend months trying to get top results.
And the results were what? How did it actually perform in this highly competitive environment?
They were frankly remarkable, Noah. Table 1 in the paper just lays it out clearly. MLE-STAR achieved medals in an astonishing 64% of these highly competitive scenarios.
64%. That's almost two-thirds.
Exactly. And breaking that down further, it secured 36% gold medals and 28% silver medals.
Wait, 36% gold on Kaggle?
36% gold. To put that in perspective, this means MLE-STAR wasn't just participating, it was consistently among the very top performers, often winning these complex ML challenges against human and other AI baselines.
That's not just impressive, that's genuinely stunning. It sounds like MLE-STAR isn't just good, it's frequently winning these complex real-world style challenges. How does that compare to other state-of-the-art AI systems or LLM agents that are also designed to build code or solve ML problems?
Yeah, the comparison is really telling. It underscores MLE-STAR's unique capabilities. According to that same Table 1, MLE-STAR significantly outperforms baselines like AID, that's another LLM-based agent, which achieved only 25.8% any medal.
Okay, so less than half MLE-STAR's rate.
Right. And even other advanced general-purpose LLMs like Gemini 2.0 Flash, which is a powerful model, achieved only 43.9% any medal, still considerably short of MLE-STAR's 64%.
Wow.
This stark difference really demonstrates that MLE-STAR is exceptionally effective at producing high-performance ML solutions. It often surpasses other cutting-edge AI systems in these tough competitive scenarios. It highlights that its specialized, iterative, knowledge-integrating approach is just far superior for complex ML engineering compared to general code generation.
So the takeaway here is just staggering. MLE-STAR is exceptionally effective at producing high-performance ML solutions, outperforming other advanced AI systems in these difficult challenges. The kind of expertise needed to win Kaggle, once limited to a few human grandmasters, seems to be becoming automatable.
That's a profound implication, yeah.
What else did the authors discover about why it's so effective? I'm really curious about the specific contributions of its methodology. What's the secret sauce? Was it the refinement? The ensembling?
This is where those ablation studies we talked about really shine. They give precise insight into the power of MLE-STAR's targeted refinement and ensembling.
Okay.
The authors conducted these detailed studies. They're presented in Table 4 and illustrated further in Figures 23 and 24 to understand the exact contribution of each component.
Right, taking pizzas out to see what happens.
Exactly. They found, for instance, that systematically removing key pre-processing steps, things like standard scalar, one-hot encoder, or imputation techniques,
Stuff data scientists use all the time.
absolutely crucial stuff for preparing raw data. Removing these significantly impacted the overall model performance. Now, this isn't just saying pre-processing is important. It empirically validates the critical importance of MLE-STAR's ability not just to include these steps, but to intelligently identify and perform targeted refinement on these specific, impactful code blocks within the pipeline.
So it knows which pre-processing steps matter most for a given problem and focuses there.
Precisely. It showed that MLE-STAR's careful attention to these foundational components, identified through its diagnostic ablation studies, was vital for its superior performance. It proves it masters the fundamentals before tackling the complex optimizations.
That's fascinating. So it's not just throwing data at an LLM, it's this smart surgical iterative refinement, honing in on the critical parts.
Okay.
And what about the ensemble strategy, combining multiple solutions? How much impact did that have on its metal count?
The authors specifically highlight its significant impact in Section 4.2. They write that the ensemble strategy alone led to a 12% higher any metal obtainment rate compared to the best single solution MLE-STAR generated.
12% just from ensembling. That's huge.
It's a remarkably significant improvement on its own. It powerfully underscores the value of combining multiple high-performing candidates. It demonstrates that MLE-STAR's innovative multi-step methodology, especially its ability to identify and refine crucial components via ablation and then strategically combine diverse solutions, is absolutely key to its superior overall performance.
So the takeaway is that MLE-STAR's innovative multi-step method, particularly its ability to find and fix the crucial parts and then combine different good ideas, is key to its amazing performance. It's the synergy of these intelligently designed components working together.
That's it exactly. It really sets it apart.
That really reinforces the idea of holistic intelligent design. Now, for many people listening, the idea of AI building AI can sound a bit, well, ominous, maybe even a little scary. Is there a role for humans in this process at all? Can MLE-STAR work with people, or is it purely designed to replace them?
That's an excellent and really important question, Noah. And the answer, according to the paper, is a resounding yes. There is a role for humans.
Okay.
Figure 5 in the paper explicitly demonstrates human intervention. It shows that MLE-STAR is designed to seamlessly incorporate human expertise and feedback into its workflow.
So you can guide it or give it hints?
Exactly. The authors emphasize this isn't a black box. It's designed to be a synergistic tool, a powerful collaborator. Furthermore, in Section H, which is titled Analysis on Data Contamination, they address a crucial related concern. Was MLE-STAR just copying existing human solutions found on Kaggle?
Yeah, that's important.
Very. They described collecting and analyzing discussion posts from the competitions and found that MLE-STAR's solutions were judged to be subtly novel compared to those generated by another powerful model, Gemini 2.0 Flash, on some problems.
Subtly novel. What does that mean exactly?
It means it wasn't just replicating known solutions. It was generating approaches that, while perhaps building on existing ideas, had elements of genuine, albeit maybe small, innovation. It indicates an ability to not only leverage external human knowledge, but also to potentially generate solutions that aren't mere copies.
That's a huge relief for anyone worried about AI completely taking over human roles. So the profound takeaway here seems to be that MLE-STAR is designed as a collaborative tool. It can learn from human experts, integrate their insights, making it a powerful partner for data scientists. Not just a replacement. It's about augmented intelligence, enhancing us, not operating totally alone.
Precisely. That's the vision presented. It's a future where humans and AI work together, each augmenting the other's capabilities, leading to potentially better outcomes than either could achieve alone. A true partnership.
That's a critical distinction and, frankly, a more hopeful vision. Okay, so that covers the how and the what. Now for the really big question, the so what. What are the real-world applications of something like MLE-STAR beyond winning programming competitions? How could this actually change things for us, for you listening?
If we connect this to the broader impacts the authors discuss in Section I in their discussion section, one of the most significant applications is the potential for truly democratizing advanced machine learning.
Democratizing, making it accessible to more people.
Exactly. Think about it. Building these high-performance models today requires an incredibly specialized and often very expensive skill set, right?
For sure. Big teams, big budgets usually.
MLE-STAR has the potential to significantly lower that barrier to entry. Imagine a small biotech startup with a groundbreaking idea but limited resources. Or a researcher in a totally different scientific field who doesn't have the budget for a whole team of data scientists. MLE-STAR could provide the sophisticated ML expertise they need. It could effectively become a virtual expert machine learning engineer on demand without the prohibitive cost and time of hiring.
So it's like putting a world-class machine learning engineer at everyone's fingertips, making cutting-edge AI accessible to a much wider range of innovators, not just the tech giants or huge research labs. That could unlock so much potential innovation.
Exactly right. This would foster innovation across countless sectors, accelerating drug discovery in healthcare, optimizing logistics and supply chains, developing new climate models in environmental science. It could truly level the playing field, allowing brilliant ideas to flourish regardless of organizational size or budget.
That's huge. And what about for companies that are already heavily invested in machine learning? The large enterprises, the ones already building AI solutions. What does this mean for them?
For them, it translates directly into accelerating ML development and discovery on a potentially unprecedented scale.
Faster, better, cheaper.
Pretty much. Instead of spending months on manual iteration, laborious debugging, incremental optimization, MLE-STAR could dramatically speed up that entire development lifecycle.
Right.
This means faster cycles for new products, new features, quicker deployment of cutting-edge AI solutions, and ultimately a much faster pace of breakthroughs. Imagine the impact in areas like personalized medicine. Rapid iteration on diagnostic models could lead to faster, more accurate diagnoses.
Or in finance, getting new predictive models out faster.
Exactly, or complex scientific modeling. By automating significant chunks of the engineering process, the human experts within these organizations can then pivot their focus. They can work on higher-level problem-solving, strategic thinking, defining entirely new frontiers for AI applications.
So it frees up human brain power for the really creative, strategic work.
It shifts human effort from the tedious, iterative tasks to the high-impact creative work. That's the potential.
That's a powerful vision for the future of innovation, speeding up the whole discovery pipeline. But okay, let's be balanced. No research, however groundbreaking, is perfect. Every study has limitations. What are the authors themselves identifying as the areas where MLE-STAR still has room to grow, or where their study might have had specific constraints?
Yeah, and the authors are commendably upfront about this. They dedicate section 6, the conclusion, to these very points.
Okay, what do they say?
First, they acknowledge that while Kaggle competitions are incredibly challenging and representative, they are also publicly accessible.
Right.
This means there's a possibility that the underlying LLMs within MLE-STAR might have already been trained on relevant discussions, code snippets, or even winning solutions from these very competitions.
The data contamination issue.
Exactly. This could subtly introduce some level of bias in the results, making it slightly less indicative of true discovery from absolute scratch versus clever synthesis of existing knowledge.
So it's like a student who aced a test, but you're not entirely sure if they just studied really well from fundamental principles, or if they maybe even implicitly had access to some old test answers beforehand. It's still impressive, but it raises a question about pure novelty. Is it a master optimizer or also a true innovator?
Precisely, Noah. It's an important nuance to keep in mind. They also note that while MLE-STAR uses LLMs as a judge for performance during its refinement process, this might not always be fully sufficient in all cases. This hints that pure human judgment, with its nuanced understanding, its ethical considerations, though the paper doesn't dive deep there, its ability to discern truly robust or elegant solutions in complex scenarios, still plays a critical, perhaps complementary role.
So the AI judge might miss some subtleties that a human expert would catch.
Potentially, yes. And lastly, they mentioned that the scalability of LLMs themselves can be a practical challenge. This points to potential limitations in applying MLE-STAR to extremely large-scale, enterprise-level problems that aren't public, require massive compute resources, or involve entirely novel problem paradigms way outside existing training data.
Okay, so while incredibly powerful, it's not a silver bullet. There are still areas where human insight, further research, and maybe just sheer scale are critical. Does this raise questions about how much we can truly automate in this complex creative process, or if there's maybe an inherent limit to what AI can discover on its own without some form of prior human-curated knowledge or guidance? It's still operating within a human-defined problem space, isn't it?
It absolutely does raise those fundamental questions, Noah, and that leads us directly into the exciting and perhaps slightly daunting avenues for future research that this paper opened up.
Where do we go from here?
Well, connecting this to the bigger picture, one critical question is, how can we further reduce MLE-STAR's reliance on that existing human-curated data in discussions? How do we push AI to truly discover novel solutions purely from first principles?
You mean, could it identify entirely new model architectures? or revolutionary data preprocessing techniques, stuff no human has thought of yet.
Exactly. Moving beyond just optimizing existing knowledge to genuinely generating new foundational knowledge, that's pushing the boundaries towards true creativity.
That's a fascinating leap. What else?
Another logical next step, building on that, would be to see if MLE-STAR could adapt to entirely new and unseen ML tasks without any prior examples or web search.
Purely from first principles.
Right. The current evaluation is on existing Kaggle problems, but applying it to truly novel, maybe proprietary industrial problems with no public precedence, or where the data structures are completely foreign, that would be the ultimate test of its adaptability and generalized problem-solving power.
Pushing it completely out of its comfort zone, basically.
And pushing the boundaries of what AI can solve autonomously.
And if it could do that,
Yeah.
if it could discover truly novel approaches from scratch for previously unsolved problems, what would that mean for broader AI advancements? It feels like we're hinting at something much bigger here.
Well, this kind of agent one that can independently engineer complex intelligence could become a foundational component for developing more generalized AI capabilities, AGI even.
Because it accelerates the very process of AI development itself.
Fundamentally. It suggests a future where AI systems can autonomously improve and innovate, potentially leading to an exponential acceleration in technological progress, far beyond anything we've ever seen.
Wow.
We could be on the cusp of an era where AI doesn't just solve problems we give it, but actively designs the solutions, designs the very intelligence that solves the problems.
Okay, let's zoom out for a moment then. What does MLE-STAR represent in the grand scheme of things? For the future of AI, for humanity, what's the big takeaway?
MLE-STAR represents a significant and genuinely exciting step in the journey of AI building AI. It's not merely automating mundane tasks, it's automating the engineering of intelligence itself.
Right.
By seamlessly integrating broad web knowledge with targeted iterative refinement and robust self-correction, it dramatically compresses the time, reduces the cost, and broadens the accessibility needed to develop high-performance machine learning. It signals a potential shift. A shift from humans being the sole architects of AI to becoming collaborators with AI in the very act of creation.
That's a profound thought.
Yeah.
So the final provocation for you, our listener, is this. If AI can now build and refine other AI models with such remarkable efficiency, and maybe even a subtle touch of novelty, what does that mean for the pace of innovation across all industries? For scientific discovery, for the very definition of what it means to be a creator, are we on the cusp of an exponential acceleration in technological progress, driven by systems that can teach themselves how to create and improve even more intelligent systems, unlocking breakthroughs we can barely imagine today? That's definitely something to mull over.
It most certainly is, Noah. It really could redefine the definition of a creator in the digital age, hinting at a future where our most complex problems might find solutions through this partnership with self-improving intelligence.
Absolutely. What an incredible deep dive into the future of AI. Thank you for guiding us through this fascinating research.
My pleasure.
And thank you, our listener, for joining us on the deep dive. We hope you feel a little more well-informed and maybe a lot more excited or perhaps thoughtfully concerned about what's coming next in the world of artificial intelligence. We'll catch you on the next deep dive.